Hi, I'm Minay, and this work was done with my wonderful collaborators when I was an intern at DeepMind. So there's been a lot of prior work that looks at how we can learn human preferences and then design policies that optimize for those preferences in single agent settings. Examples include learning human rewards using inverse reinforcement learning or active preference learning, or directly imitating desirable human behavior via imitation learning methods. And in practice, these methods have been used quite successfully to teach robots how we'd like to be fed, or teach cars how aggressively we'd like them to drive for us. And probably the most successful and famous use case is ChatGPT, where it was trained to generate text based on human preference feedback. So what happens if we scale this up? Now let's consider the scenario where you have a community of people who are each represented by their AI assistant, something like a hyper-intelligent Siri. Imagine that these assistants are all independently trying to optimize their humans' preferences. At first glance, this seems to be a straightforward, non-problematic scaling up of the single agent setting. But something's missing here. Let's say that these AI assistants are autonomous cars, and for simplicity, let's say that each person's goal is to minimize their commute time. Let's also say that a new bridge was built that cuts through a lot of the roads and acts as a shortcut. So if every car tries to minimize commute time, it's been famously shown that this can lead to increased congestion because all cars would try to take the shortcut. This is the exact opposite result of what the human preferences were, and this paradox is called Brace's paradox. This result is not a result of reward hacking or suboptimal driving policies, but as a direct result of rational behavior. So there's really a deeper problem here where the solution is not to trivially improve the local objective or mitigate reward hacking. We argue that it's actually not enough to optimize for local objectives alone. Instead, each agent must optimize for a system-level global objective that measures some system-wide metric that we might care about. For instance, going back to the driving example, the global objective would be to minimize average commute time. Thus, when we think about how we can align our assistants to our values in a multi-agent setting, this problem is actually a multi-objective problem. And this is because each agent must consider both their human's objective as well as some global objective, and they must make some trade-off between the two. Finally, we also recognize that different communities may want different global objectives that don't have to be about maximizing welfare. So they could reflect societal values such as minimizing carbon emissions or minimizing inequity on the roads. Thus, our goal in this work is to align multi-agent systems that have local objectives with an arbitrary global objective. So how are we going to do this? So each time we change the global objective, we're going to modify each agent's local objectives so that we get better performance on our global one. So here we are going to assume that we linearly modify agent objectives. The key here, though, is that we want to do this automatically, so no human supervision is needed in finding parameters alpha and beta. We also don't want to deviate too much from our local objectives. So if your assistant ignored your objective in pursuit of a communal one every time, you'd probably not want to use that assistant anymore. So we want to modify each objective as little as possible. So we build upon an algorithm called D3C, which was published in Gemp et al. In 2022. This is a decentralized multi-agent learning algorithm that minimizes the price of anarchy with respect to welfare. So in other words, D3C automatically modifies local objectives in order to optimize for a fixed global objective, which is welfare, or the sum of local objectives. In this work, we're going to examine the extent to which D3C can generalize to arbitrary global objectives, and then actually use it to optimize for different global objectives that produce different desirable system-level behaviors. But first, let me explain how this algorithm works. At the heart of D3C, agents change their local rewards through gifting. For simplicity, let's assume that there are only two agents. So each agent has their local reward, for instance, the preferences of their humans, and we assume that this is given to us. Agent 1 can decide to gift some of the reward that they get to other agents, denoted by a coefficient A12. They will then keep the rest of their reward, denoted by A11. Importantly, the sum of A11 and A12 must equal 1, meaning that agent 1 cannot create more reward out of thin air or cannot throw away reward either. And of course, agent 2 can do the same as well. So each agent's new local reward will be updated as a linear combination of all agents' rewards. So remember how I said that we will optimize for the global objective by automatically modifying the local objective, where we have those coefficients alpha and beta? So this is how we modify the local rewards, through gifting. Importantly, you can see that each agent's reward is a combination of their own as well as the other agents. So this is how agents can influence each other. So if the other agent is doing a good job, you can reward them. If they're not doing a good job, don't reward them. This is also what we call local mechanism design. So how does each agent find their sharing parameters? Well, each agent will optimize for parameters that maximizes the global objective via gradient ascent. So for instance, agent 1 is in charge of parameters A11 and A12, and will find values for those that maximize the global objective. So essentially, each agent wears two hats in this algorithm. One of the hats they wear is the local mechanism designer, where they change their local objective to optimize the global objective. And then for the other hat, they act as a local policy optimizer. So here they do the normal thing that RL agents do, where they optimize this updated local objective in order to solve for a policy. And each agent in the multi-agent system will do this simultaneously. And they will all continually repeat both of these steps until they reach convergence in optimizing the global objective. We're still missing something though. So in the beginning, I talked about how we want to deviate from our local objectives as little as possible while optimizing for a global one, because we want to respect the original human preferences as much as possible. So we enforce this in two ways. So first, we initialize the sharing parameters A11, A12, etc. to be selfish, meaning that each agent primarily will receive their own reward. And this is equivalent to each agent optimizing for their own local objective without caring too much about other agents' objectives. Second, we enforce a KL penalty so that the sharing weights don't deviate too far from these original selfish parameters as they update their sharing weights. So let's go back to the big picture. Our goal is to align multi-agent systems that have local objectives with an arbitrary global objective. D3C is an algorithm that we just saw that can help us do that, but it's only been studied for the case of a single global objective, which is welfare. So we asked two questions in our evaluation. First, what global objectives can D3C optimize for? Can it optimize for any global objectives, or are there some restrictions? Second, we ask whether we can use D3C to produce different desirable system-level behaviors in complex multi-agent domains by optimizing for different global objectives. We start with the first question, and we assess this in a two-player prisoner's dilemma-like game where our local and global objectives are defined as losses instead of rewards. So each player's action space is continuous and lies between 0 and 1. On the right, we can visualize the space of joint strategies, where on the x-axis, we have the space of strategies that player 1 can choose, and on the y-axis, we have the space of strategies that player 2 can choose. Each agent's local objective is defined like so it's a symmetric game. And for any strategy chosen by player 2, player 1 is incentivized to play 0, which is equivalent to defect in prisoner's dilemma, and vice versa. So when both players choose 0, this is the Nash equilibrium solution, and the maximum welfare solution is when both players choose to play 0.5. For our global objectives, we simply define it as the square distance to a goal joint strategy. We can then sample goal joint strategies from this space shown on the right, which is shown as the white dots. So if we imagine the color white to symbolize 0 loss, if D3C can truly optimize for any arbitrary global objective, then we should be able to get 0 loss for each goal joint strategy that we sample, and the entire square should basically look white. Since this domain is simple enough, we were able to analytically solve for which global objectives or goal joint actions D3C should be able to achieve 0 loss on. And this is our result. So white represents reachable, whereas blue represents areas that are theoretically not reachable by D3C. And you can see that not all areas are reachable. And the dark blue areas represent areas that you would need to create or destroy loss in order to reach. So when objectives are defined as rewards, this is equivalent to agents creating or destroying reward. So this violates our assumption of budget balance where the sharing weights must equal exactly 1. We also show an empirical solution where we ran D3C with each of these joint strategies as a goal joint strategy. So the figure on the right shows the losses for each global objective across 3 random seeds. And you can see that the white regions on the off diagonals stay white and have 0 loss. However, the loss starts to increase as we approach the upper left and lower right corners. So from these results, we can observe that analytically, D3C can't really optimize for global objectives whose solutions aren't reachable with the budget balance constraint. But in practice, empirically, we can do a pretty good job of achieving low loss or high reward on theoretically unreachable global objectives, as shown by the light blue colored squares. So next, we investigate whether we can use D3C to produce meaningfully different desirable behaviors. And in the paper, we focus on 3 domains, but for this talk, I'm going to focus on the most complex one, which is cleanup. So cleanup is a 7-player social dilemma. Objectives are defined as rewards instead of losses here. So agents must eat apples in order to gain reward, but apples only spawn if a nearby river is free of dirt. So agents must also learn to clean the river in order to grow the apples. So explicitly, the local objective here for each agent is that they get a +1 reward when they eat 1 apple. And this is a challenging learning problem because agents must learn to be selfless and clean the river to grow apples and then eat them and earn reward. So current algorithms that are commonly used to solve this problem include independent RL, where agents just selfishly maximize their own local reward. This leads to policies where agents never learn to clean the river because they're selfish. We also have a pro-social algorithm where all agents maximize the total local reward. This leads to a much more effective policy where agents learn to clean the river, but this results in an unequal division of labor, where you normally have 2 to 3 agents that are designated river cleaners, whereas the other agents get to harvest apples. So none of these are really that satisfactory, and we ask if we can get a fairer policy than the pro-social one, where agents take turns cleaning the river. So we experiment with different global objectives to try and get this behavior. And the main one that we look at is welfare plus equity, which is the sum over the welfare objective, as well as the equity objective that tries to basically minimize the absolute difference from agent I's reward to the group's average reward. We also include the welfare and equity objectives as ablations. So let's first look at how agents perform when we measure welfare. On the x-axis is number of training iterations, and on the y-axis is average welfare. So pro-social, which is the red line, is currently the state-of-the-art baseline for this objective, and we can see that agents trained with welfare plus equity, which is the green line, also achieve comparably high welfare, meaning that some agents have also learned to clean the river. You can see that agents trained just the welfare objective, which is the blue line, don't do very well, and this is pretty surprising. You can see that actually agents trained with the equity objective, which is the orange line, do better on welfare because they are selfless and learn to clean the river. I'd say another takeaway from this graph is that the different choices of global objectives can indeed produce different systemic behaviors when using D3C, but the choice of global objective is not obvious. So for instance, here, agents trained with the global objective welfare don't really end up maximizing it very well. So global objectives must be chosen carefully. When we change the metric and now look at how agents perform when we measure equity, we can see that now agents trained with the welfare and equity objectives, so the blue and orange lines, who are getting close to average 0 reward, are very equal or equitable because everyone isn't getting much reward. But notably, you can see that the welfare plus equity objective has a much higher equity than the pro-social one. And recall that these 2 lines were getting the highest rewards. So this implies that the welfare plus equity objectives learned a fairer policy where some of the agents learned to take turns cleaning the river. And in practice, we did see that some agents were able to take turns cleaning the river and harvesting apples with this global objective. Finally, we can also see how agents learn to trade off between local and global objectives. So the x-axis of each plot represents the 3 different global objectives, whereas the y-axis represents the local reward. The blue dotted lines represent the empirical maximum global and local reward. And we can see that over training time, agents heavily prioritize the global reward for the first 2 objectives, whereas for the 3rd objective, they learn to trade off much better. So in sum, our findings motivate the value of enabling a multi-agent system to really be more efficiently repurposed for different global objectives. And this opens up a lot of interesting follow-up questions for exploration.